So now we are going to discuss about the last topic of this last subtopic, implementation of MPC. After deciding all these things, how to implement a model predictive controller. So implementation of model predictive controller. It has 8 steps. First step is initial controller design. Second design is pretest activity. Third step is plan test. Fourth step is model development. Fifth step is control system design and simulation. Sixth step is operator interface design and operator training. Seventh step is installation and commissioning. And the last step is measuring results and monitoring performance. So step 1, initial controller design. Okay. So in initial controller design, the first thing that we have to do is we have to select the control, or we have to identify the controlled variables, manipulated variable, and the measured disturbance variable. These three we have to identify. So after selecting this one, we have to determine the structure of MPC control system by using these three. After selecting the controlled, manipulated, and measured disturbance variables, we have to select the structure of MPC control system. Okay. So in order to determine the structure of MPC control system, we have to apply process knowledge and control objective. Okay, we have to thoroughly know about the process. The process knowledge is very important, and we have to know the control objectives. Okay, so in typical application, so here we are discussing about the maximum manipulating variable and etc. So in typical application, number of controlled variable is less than or equal to 40. In typical normal situation, in a plant, number of controlled variables is less than or equal to 40, and number of manipulated variable is less than or equal to 20. Okay, that is normally smaller is less than or equal to 40 and smaller is less than or equal to 20. Additional output variable can be added to MPC control structure later if necessary. If you want to add an additional one, that is possible in MPC control structure. Now step 2 is pretest activity. Okay, so here the plant instrumentation is checked to ensure that it is working properly. That is very important. Okay, so what are the things that we have to check? We have to check the faulty sensors, whether faulty sensors are there or not, sticking control words, and etc. Okay, and if these are there, we have to take some remedial actions. Decision has to be taken to install sensors for some process variables that are not currently measured. If you are not measuring a controlled variable, then we have to take some decision to remove that sensor or not. So that we have to take some decision regarding it. Okay. Now, along with these testings, we have to do some preliminary experimental tests to estimate the steady state gain and approximate settling time, because I told you n into delta t must be greater than or equal to ts. Okay, so we have to know the settling time. So during this pretest activity itself, we can do some preliminary experimental test where we are not checking any dynamics or not, we are checking what is the settling time. Okay, and we are not checking whether it is oscillatory, whether it is the initial time constant, etc. We are not checking. Okay, so here we are estimating the steady state gain and settling time. Okay, steady state gain is also very important, because anyway we are measuring the settling time. So if we know the settling time, then we know the settling value. Okay, that settling value is known as steady state value divided by the steady state value of input is the steady state gain if initial conditions are 0. Okay, now Please not thoroughly check the performance of DCS control system. That is also very important because normally in plant DCS controller is used. So thoroughly check the performance of DCS control system. Okay, and if necessary, retune or reconfigure the control loop if necessary. If the basic instrumentation and DCS control system do not function properly, the MPC strategy will be ineffective. So this is very important. The MPC control strategy is ineffective if the basic instrumentation and DCS control system is not functioning properly. Each manipulated variable, okay, this is actually the continuation of previous one, that is how to calculate the steady state gain and the settling time. So for the purpose, each manipulated variable is bumped at least once by making a small step change. Provide a small step change to each manipulating variable. Then by using that, the steady state gains and settling times are estimated by using this small step change. Each measured disturbance variables are also bumped if possible. Okay, we have to know the steady state gain towards the measured disturbance. If it is not possible, then by using the previous history we can find the steady state gain and the time constant. We can utilize the historical data if it is disturbance. If it is a manipulative variable, we have to do some experiment. Now step 3 is plant test. Here we are using some dynamic experimental data. Means here we are finding the dynamic model. So the dynamic model for the MPC calculations is developed from data collected during the special plant test. So this one is a crucial step, very important step. Actually it is time consuming. Okay, it typically requires days or even weeks, so it's a time consuming step. Okay, so the test duration depends upon the settling time of the output and the number of MVs and DVs. Okay, in previous step we calculated the settling time. Okay, so here this plant test is depending upon the settling time and also the number of manipulating variable and the disturbance variable. So excitation for the plant test usually consists of changing an input variable or a disturbance variable from one value to another. Again we are giving step input. Okay, but here the situation is different. Here the step input is given to find the dynamic model. Okay, so we have to note down each and every point, not the final settling value. So either a series of step changes with a different duration, we are doing this thing. So here in traditional industry, each manipulating variable or disturbance variables are changed individually, one by one, not simultaneously. Magnitude of the step changes are carefully selected. Okay, why? If the step change is very small, then we can notice the steady state change, but we can't easily note down each point of the dynamic variation. That is not possible. And one more thing is that if the step change is small, the effect of noise is very good. Now for large move, the possibility of saturation will be there. The nonlinear constraints, nonlinear behavior, etc. will come into the picture. Okay, so we have to suitably select the magnitude of step change. Magnitude of the maximum allowable input change can be estimated from the knowledge of output constraints and the estimated steady state gains from the pretest. So the data collected from step 2 can be used for this purpose. Example, say delta uj, the step change of jth input, its maximum value denotes the maximum change that can be made in uj without violating a constraint for yi. Then delta uj maximum is equal to delta yi maximum divided by kij. Means yi means ith output, its step change, take its step change. Now take the maximum value divided by the gain, the steady state gain connecting jth input and ith output, that is Kij. So it will give the maximum value or the bound of the step change of jth input, jth manipulating variable. So now the duration of longest step test is equal to Tmax. Duration of longest step test is equal to Tmax, means in step 2 we have the settling time of each input and output combination. Take is the largest value. So the duration of the longest step is duration of the longest step test is taken as the largest settling time Tmax. In order to ensure that the sufficient data are obtained for model identification, each input variable is typically moved 8 to 15 times. So you can see that it will again increase the step 3 duration. Each input is repeated, each input step change is repeated 8 to 15 times. Okay, we can reduce that by using input masking, that is possible. Okay, but typically the t test is equal to, the total test is equal to 6 into r plus p into t max, where t max is the largest settling time, into 6 into r plus p, where r is the number of input and p is the number of measured disturbance. Okay, we are also using measured disturbance. So this one is the test duration of Planck test. Now the fourth step is model development. So now we have a number of data like steady state gain, settling time. Now we have dynamic variables. So by using all these we can develop the dynamic model. Okay, we can develop the model of the process. We can develop any type of model like step response model, impulse response model, time constant model, steady state model, polynomial form, etc., etc. But here in this particular explanation we are using step response model. So in this one it is very important to eliminate periods of test data during which planned upsets or other abnormal situations have occurred, so that we can eliminate. Okay, like control valve saturation. Decision to omit portions of the test data are based on visual inspection of the data, knowledge of the process and experience. So if you are omitting a particular portion, first we have to visually inspect that data. Okay, we have to apply our knowledge about the process, and we have to apply, definitely we can apply our experience also. Okay, so please note, parameter estimation is usually based on least square estimation. So here we are not doing any parameter estimation or adaptive, we are not designing any adaptive controller. Okay, but if we model prediction, for model prediction first we have to know model. You know, to identify model, either we can use the transfer function derivation process or we can use parameter estimation. Okay, so if you are using parameter estimation, least square estimation is normally used. Okay, now step 5, that is model prediction, design of model predictive controller. So control system design and simulation. So the model predictive control design is based on the control and optimization objectives, process constraints and dynamic model of the process. So throughout up to this point we have discussed all these things, how to utilize the dynamic model, what is the importance of objectives, etc. So by using all these things we have to design model predictive controller. Preliminary control system designs from step 1 is critically evaluated and modified if necessary. So we have step 1, 2, etc. Not this step 1, we discussed about 7 steps used for model predictive control design. So these 7 steps are critically evaluated in each step, and if necessary we have to repeat it. Okay. Then MPC design parameters are selected, including the sampling period, weighing factor and the control and prediction horizon. Closed loop system is simulated. This is also very important. After designing we have to simulate it, we have to test it. So closed loop system is simulated using the identified process model and a wide variety of process conditions to evaluate control system performance. And if necessary we can do some fine tuning on the design model predictive controller. Okay, After designing the model predictive controller, the step 6 is operator interface design and operator training, because the operator is going to use or operator is going to run the model predictive controller. So he or she must have thorough knowledge about the model predictive controller, how to run that model predictive controller, how to operate that model predictive controller. So the plant operator plays a key role in manufacturing plant. So it is important that the MPC operator interface meet their needs. Operator training is also very important. A number of training sections are very important for operator. He must know how to operate that model predictive controller. Okay, so he or she has to know the model predictive control concepts such as predictive control, multivariable interaction, and constraint handlings are very different from conventional regulatory control concepts. Okay. Now the second last step is installation and commissioning. Once we have model predictive controller and once the operator is uh, familiar with the model predictive controller, then we can install the model predictive controller and commission it. So a number of steps are there. After a MPC control system is installed, it is first evaluated in a prediction mode. First we have to evaluate. After installation, we have to evaluate that model predictive control in a prediction mode. Model predictions are compared with the measurements. Then we have to compare the predictions of measurement. So we have the bias correction. So after some time, the predicted value and the actual value must be same. Okay. So that we have to do. The important thing is, even if we are running model predictive controller, the actual system is controlled by using the conventional control system. Okay, here we are just evaluating it. That one is not completion. Okay. After the output predictions are judged to be satisfactory, the controlled MPC control moves are evaluated to see if they are reasonable. After the predictions are satisfactory, what is the next step? We have to check whether the model predictive control output is satisfactory. Then, if all these are satisfactory, the MPC software is evaluated during the closed loop operation. Now we can use the closed loop. That means just give the model predictive control input, manipulating variable to the process and check whether it is satisfactory. Okay. If all these four are satisfactory, what are the four steps? First one, run the model predictive control in the prediction mode. What is the second step? Check whether the predictions are accurate or not. If it is accurate, what is the third step? Check whether it is giving satisfactory control output, whether the model predictive control is giving the satisfactory control output. But please note, still the conversion control system is used to run the process. Okay. Now what is the final step? Now we are running the closed loop, means give the control output to the process and check whether the model predictive controller is capable to run the process satisfactorily. Then if it is satisfactory running, no problem. Otherwise, we have to give a small adjustment. In some situations, small adjustment is required. So if it is necessary, provide small parameter adjustment, fine tuning that we can provide. After these 5 steps, we can commission the model predictive control. So the commissioning period typically requires some troubleshooting and take as long as or even longer than the plant test. I told you plant test require days or weeks. So commissioning require more than that, because regularly we have to check. For a long period we have to check whether it is working satisfactorily. And if it is 100% accurate, then we can commission. Now after commissioning, we have step 8, measuring results and monitoring performance. After commissioning, still we have to monitor the performance of the system. So the evaluation of MPC system performance is not easy. There is no monitoring strategies that are not available. Okay. Useful diagram information is provided by basic statistics such as the means and standard deviation for both measured variable and calculated quantities such as control arrays and model residues. Okay. After commissioning, still we are evaluating model prediction. We are measuring residues. Okay. If you have residues, we can take it as a statistical data. We can take the mean deviation and the standard deviation. Okay. So means after commissioning, we are checking the performance of the model predictive controller. Okay. But the problem is there is no widely accepted matrices, but still we can use classical matrices such as uh, integrated absolute error index, overshoot, settling time, and degree of oscillation provide an incomplete picture of small MPC performance, etc. Evaluation of MPC performance should include measures of whether these objectives have been realized. Economically meaningful measures such as product quality, throughput, or energy cost should be calculated before and after the MPC system commission. Okay. MPC system performance should be monitored on a regular basis to ensure that the performance does not degrade owing to a change in process, instrumentation, or process condition, including disturbance. So we have to regularly monitor the performance of model predictive controller. If performance becomes significantly worse, returning the controller or re-identifying all or part of the process model may be required. Development of MPC monitoring strategies is an active research area. I told you, still we don't have a monitoring strategies. Still, this one is a research area. Okay. So I am stopping my discussion about the model predictive controller. Okay. And I am expressing my sincere thanks to Dr. Shaima Madam for giving an opportunity to present this topic in front of uh, this uh, dais. So these are the references used for the presentation. Seaborg, Edgar, Millicham, and Doyle, Process Dynamics and Control, Wiley third edition. Okay, please note the entire diagram, explanation, etc. All are taken from this textbook. Okay, thank you.